day, viewers. Welcome to another broadcast of Science Spectrum with Dawn. And this is the second discourse in Physics Classic on dependence of pressure at a depth. Alright, so stay tuned as I talk more about this. Now, you must have been informed or pre-informed earlier that when you go down into a fluid, when you're submerged down in the fluid, the pressure right at the bottom of the fluid where you are, or at that level of the fluid where you are above the surface, increases. So as the height increases below the surface of the liquid, that as you go down into the fluid, pressure increases by a certain amount. And that amount is really the weight of the fluid, or the column of the fluid above you that you just have to carry. And of course, as you go down into the ocean, as the height increases, so to speak, right? Then what it implies is that the pressure on you increases by a certain amount, and that amount is equals to the density of the fluid that you are submerged in times g. G stands for gravitational acceleration, and of course times also the height where you are below the surface of the fluid. All right, now if I draw a cylinder like so this is a cylinder, it's filled with a fluid. Take any fluid. This could be, for instance, water. It could even be soft drink or even red wine, like the way Pascal did. And let the liquid line be here. So this is all filled with a fluid. So this fluid has a density, rho of the fluid. And let's assume that since this object is cylindrical, let the surface area at the top and at the bottom be the same. So I'll represent that with an A. Now clearly, this liquid is right at the surface, is exposed to the atmosphere. So it feels a force. I'll call that the force exerted on it at the top of the fluid. Then this is the surface area. Now clearly, because it's just exposed to the atmosphere, the pressure right here is really what we call the atmospheric pressure. That is the pressure due to the column of air above the surface of the liquid. All right, then let me call this level H, from the surface of the liquid to the bottom of the fluid, H. Now, right at the bottom of the fluid, there is even a larger force, which is called the force at the bottom. And the force is larger simply because of one thing. This force has to bear the force at the top plus the weight of the fluid itself. So if I write this mathematically, the force at the bottom of the fluid equals the force at the top plus the weight of the fluid. Weight of the fluid that this water at this point has to carry. Alright, so if you recall, pressure is simply the perpendicular component of the force per unit area on which the force acts. So if you cross multiply this, you figure out that force is really the pressure times the surface area. So what's the pressure at the top then? The pressure at the top has to be, the force at the top has to be the atmospheric pressure, since it's exposed to the atmosphere, times the surface area of the cylinder. Plus, then what's the weight of the fluid? If you recall, weight is the mass of the object times gravitational acceleration. And this G is 9.81 meter per second squared, and roughly, oftentimes we use 10 meter per second squared. Now the mass itself could be redefined as the product of the density times the volume. That's mass itself, rho v. Then we have a g. So all of this still defines the weight of the fluid. But volume itself is a product of the surface area times the height times this column, h. So this is volume. So I have rho and I have g. So if we would redefine what the weight of the fluid is, it has to be the density of the fluid, rho fluid, times A, the surface area, times H, which defines the volume, times G, which stands for this constant you see here. So the weight of the fluid has to be density of the fluid times its surface area times the height, which defines the volume. Then this is times G. So this is the mass, rho AH, and this is G. That's the weight. All right, so this equals the force at the bottom. Now, what I'm particular about is, I do know that the atmospheric pressure right here, since it's exposed, the atmospheric pressure right here is 1 atmosphere. And of course, I could convert this to SI units. This is exactly 1.03 times 10 raised to the power 5 Pascal. And of course, there are other units. This could also be in Torricelli. So its equivalent is 760 millimeters of mercury. So this is 760 millimeters of mercury, or in Torricelli. And of course, if you use English units, this is exactly 14.7 pounds per square inch. But I'll work with the SI units, that's in Pascal. All right, so the emphasis now is, I know the pressure at the top, right, since it's exposed to the atmosphere. What's the pressure right at this depth below the surface of the liquid? So to get it done, if you recall, pressure is really the force per unit area. So the force at the bottom, divided by the area, really defines what the pressure at the bottom is. Right? So what the force at the bottom is clearly this term. So the force that the term of is the atmospheric pressure times the surface area plus the density of the fluid times A times H times G. And of course, I could divide, since A is common, I could divide through by A. This defines the pressure at the bottom. Now, if we break this down further, this becomes this term divided by the common denominator, which is the surface area. So I'm left with the pressure, the atmospheric pressure, since the A cancels out, then plus this term divides A. I lose the A, so I'm left with rho, density of the fluid, times G times H. This defines the pressure at the bottom. And of course, this does not only hold for the bottom or the depth of the fluid. It also holds true for any 2 points in the fluid. Because if you increase the depth by H, as H increases, the pressure on the fluid increases by this amount, which is rho. It increases by this amount, so to speak, by rho GH. So for every height you are submerged into a fluid, the pressure increases by this. So the sum of the two gives you the total pressure right at the bottom where you are. All right, you need to beam this for a while, and this, while I clean this up, and I'm sticking some numbers to have a feel of this. All right. So you may beam this for a while. All right. So let me do a working example, sticking some numbers to have a feel of this. Now, so take for example a given. The Titanic was found in 1985 at a depth of 4,000 meters. And of course, it was found in the North Atlantic Ocean. So I'll take some quantities there. The depth at which the Atlantic was found below the surface of the North Atlantic is roughly 4,000 meters. And of course, I do know that the density of water, which is the fluid in this case, is 1,000 kilogram per cubic meter, roughly. Actually, it's 1025 kilogram per cubic meter. Now, the emphasis is this. I know what H is. Of course, G is a given. It's roughly 10. The density of water is also given to be 1,000. And I do know that the atmospheric pressure is clearly 1 atmosphere. So the question now is, what is the pressure at the bottom of the Atlantic where the Titanic was found? All right. So clearly, to make the job easier, I will stick in this formula and simply insert these quantities, these values for each of the quantities, and of course I will number crunch and I'll get what the answer is. So clearly, the pressure at the bottom equals, using this formula now, equals the atmospheric pressure, which is 1.03 times 10 raised to the power 5 Pascal. The next SI unit is the same as 1 atmosphere, the same as 760 millimeters of mercury or Torricelli, or 14.7 pounds per square inch. Plus, the density of the fluid, which is water, is 1,000. Just keep the units at the end of the day. G is, let's use roughly 10. And the height is 4,000. 4,000. So clearly, this would come out also in Pascal. Because Pascal itself is Newton per square meter. So I had a Pascal here. For density, that's kilogram per cubic meter. G is meter per second squared. And of course, height is in meter. Right? Okay? Newton per square meter. Density is kilogram per cubic meter. G is meter per second squared. Alright, so it turns out to be that the unit is still Pascal. Alright, so to get this job done, how is it like so? Kilogram meter per second squared. That's Newton is mass times acceleration. That's kilogram meter per second squared. This term is Newton. Kilogram meter per second squared is Newton. So this term, you see right here, is Newton. So meter in cubic meter, I'm left with squared meter. So if this term is Newton, Newton per squared meter is the same as what you have here, which is Pascal. Alright. So now, to get the job done, I have 1.03 times 10 raised to the power 5 plus. Now, how many powers of 10? How many zeros do I have? 1, this is 3, 4, 5, 6, 7. Alright, so I have 4. Okay, let me use okay, let me make these powers the same as 5, 5 on both sides. So this is if I stick in 2 zeros, so this becomes 10 raised to the power 5. So I've deleted 2 zeros now. So I'm left with 40 times 10. So that is the same as 400. So the emphasis for making the powers of 10 equal is just to factor out the power of 10. So clearly, this becomes, I will factor out 10 raised to the power 5, open the brackets. This term divided by 10 raised to the power 5, 10 to the power 5 cancels out. So I'm left with 1.03. The sign is a plus. Plus times what gives me a plus is still a plus. This term divided by 10 to the power 5, 10 to the power 5 cancels out, so I'm left with 400. And everything turns out to be in Pascal. So if you sum this up, clearly you want to be in this for a while I clean this up. So if you sum this up, it turns out to be that we have 400. Just say 401.03. So this is 401.03 times 10 raised to the power 5 Pascal. And of course, I could make the job easier. I could convert this to kilo Pascal. So a kilo implies I'll drop this, I'll make this power 3. So what it implies is if I move 2 decimal places to the right, this power drops by 2. So I have 40103 times 10 raised to the power 3 Pascal. Yeah, the same, yeah. So what it simply implies is that this 10 raised to the power 3 is what we call kilo Pascal. So the answer is really this term in kilo Pascal. Alright, now I said earlier that this formula, the pressure at the bottom, which equals atmospheric pressure plus the density of the fluid times G times H. I said it holds true not just for a depth, not just at a depth below the surface of the liquid. It could hold for any 2 points right in the fluid. So if we do that, you want to bring this for a while, and I will clean this up. Crunch. Good to go. Alright. So that formula holds true not just at a depth or at the bottom, but it holds true. So this is the same picture, a cylinder like so. So this is the liquid line. Let the liquid line be here. Alright, okay. So let's say I have an object that's cubical shape. Alright. So from here to the surface of the object, this object is submerged now. Let me represent this with a D. Okay? But the height is H. It's already submerged. So clearly the pressure at the top of this object is no longer 1 atmosphere, it's submerged. So it's 1 atmosphere with the weight of the fluid that is just right above it. Alright. Now, so if I call this point H1 and I call this point H2, this is point 1, this is point 2. And this fluid that this solid is submerged has a density roughly. So clearly the pressure at this second position is really the pressure at the first position plus the density of the fluid times G, and of course times this column of H. So this holds true for any heights, any 2 points in the fluid. Why? Because as H increases, as you go down into the fluid, pressure increases by an amount of rho of the fluid times G times H. Alright, I need to wrap it up here for the sake of time. Thank you for staying tuned.